Hello, my name is Neco. I'm a Bok Honor Scholar at the RSAA, and today I'm going to be talking about one of the key results of my thesis, which answers the question of on which scale do we measure magnetic fields becoming most concentrated in the kinematic phase of the small-scale dynamo. We know magnetic fields are a very ubiquitous phenomena, with the universe being in a very magnetized state based on our observations. Recent studies have been probing the M82 starburst galaxy, finding that there's both a small-scale and a large-scale component to the magnetic field. They further estimate that the turbulent kinetic and the turbulent magnetic energies are in close equipartition up to about 2 kiloparsecs. We know that magnetic fields in the early universe are much weaker than these observations of magnetic fields in the present day. And therefore, for us to be able to understand magnetic fields in the present day, we need to be able to explain how magnetic fields become amplified and sustained at the levels that we observe them in the present day. Now, a plausible theory that explains how magnetic fields are able to amplify is the small-scale turbulent dynamo. Specifically, the stretch-twist-fold model proposed by Weinstein and Zeldovich explains how magnetic fields are able to amplify in a very simple turbulent environment. Theories predict very precisely, using this sort of framework, where magnetic fields become most concentrated. Batchelor in 1950 proposed that magnetic fields should become concentrated at the turbulent viscous scale, because the viscous eddies are the fastest and therefore most dominantly amplify magnetic fields. Alternatively, more recent studies suggest that the magnetic field should become concentrated at the resistive scale, where magnetic fields dissipate instead. Now, in order for us to confirm what the principal dependence of the peak scale is it the viscous or is it the resistive scale, we ran simulations testing these theories. We solved 3D non-ideal MHD equations using a modified version of the Flash simulation code, and we ran subsonic simulations probing different parameters in the plasma. We changed the Reynolds number, the magnetic Reynolds number, and the Prandtl number, probing the plasma in order to determine what this principal dependence is. On the right-hand side, I showed two of our simulations. On the top panel, I show a simulation where the Reynolds number has been fixed at 500. And on the bottom, we have increased the hydrodynamic Reynolds number to 1500. Now, at first, immediately what we notice is that in the higher Reynolds number simulation, the energy becomes concentrated at smaller scales. And this is true for both the kinetic and the magnetic energy. Next, we also notice that the magnetic energy amplifies. We see a growth in the magnetic energy over time. Looking at the magnetic energy relative to the kinetic energy, at first, the magnetic energy is much, much weaker, orders of magnitude weaker than the turbulent kinetic energy. Almost immediately, we go into this exponential phase of the dynamo, this kinematic phase where the magnetic field lines are amplifying very efficiently. And this continues until there's enough energy in the magnetic field in order to resist until the Lorentz force has a back reaction on the turbulent velocity field. And then we go through this nonlinear phase, transitioning into the saturated phase. We measure that there's both a dependence of the growth rate and the saturated level on the Reynolds number. Now, the small-scale turbulent dynamo is a very multi-scale phenomenon. What I mean by that is energy is distributed over many different scales, but we are able to characterize the kind of small-scale turbulent dynamo that we are observing by defining a few key scales. Specifically, we are able to measure the viscous, the resistive, and the scale where magnetic fields are most concentrated using a couple of different models. At first, we fit a model that we propose, a model for the kinetic energy spectra that is motivated by the shape of the spectra. We have a power law and then a dissipation term. And then for the magnetic fields, we use a solution to the Cousins-Sieve equation, where again, we have a power law, and then we have this modified Bessel function of the second kind, which is derived by Kohlschreiber and Anderson in 1992. And we fit this model to our energy spectra and measure these scales in the problem. And then we study the dependencies between these scales. So we compare the scale where magnetic fields are most concentrated for all our simulations against where we measure the viscous and the resistive scales being. First, we notice that there's a dichotomy taking place. For simulations where the Reynolds number is low, where the flow is stochastic and turbulent field is underdeveloped, the flow behaves very differently as opposed to when the Reynolds number is much larger than 100. When the Reynolds number is larger, we have sufficiently developed turbulence, and we find that there's a linear dependence of the peak scale on the resistive scale. And specifically, we found that the constant of proportionality that connects the peak scale with the resistive scale is bounded by the cousins of exponent. And over here, it's bounded because alpha mag is 3/2 for the small scale turbulent dynamo. And then when one derives this relation, we find that this fraction is always less than 1. It's bounded between 0 and 1. So that's why we say it's bounded by the cousins of exponent. So we found previously that the principal dependence is on the resistive scale. But when we have a look at this peak scale on the viscous scale, we find that there are a couple of things taking place. First, when we ran our simulations with a fixed Reynolds number, on the right-hand side, the Reynolds number has been fixed at 500 and on the left at 10. When we keep the Reynolds number fixed and we change the magnetic Reynolds number, we are able to change the peak scale. So this immediately suggests that the peak scale does not depend upon the viscous scale. So in order to understand what's taking place over here, we have a look at the equations again. And over here, what we find is this is actually just an echo of the previous result. When the peak scale depends upon the resistive scale, and we keep the magnetic Reynolds number fixed, as we have done in these simulations, the magnetic Reynolds number is 3000, then we find that it will look like K peak depends upon K nu, but this is again just a result of the dependence upon the resistive scale. So this answers the question. The peak scale depends upon the resistive scale. When you change the scale where magnetic fields dissipate, you will change where they are most concentrated. So I want to thank you for listening. I'll put up my summary slides. If you have any questions, please feel free to contact me on my email. Thank you.